bond conductor should have a lower impedance, and a ground electrode conductor may have some inductance. However, it is not accurate to say that a bond conductor is a short circuit or that a ground electrode conductor is an inductor. Bond conductors are intended to provide a low impedance path between metal objects to equalize their electrical potential. They are typically made of copper or aluminum and are sized to carry the expected fault current. While they should have a low impedance, they are not intended to be a short circuit. Ground electrode conductors connect the grounding system to the earth. They may have some inductance due to their length and shape. However, the inductance of a ground electrode conductor is typically negligible compared to its resistance. While some engineering documents may use the terms short circuit or inductor loosely in the context of bond conductors and ground electrode conductors, these terms do not accurately reflect the intended function and characteristics of these components. The terms bond and ground have specific meanings in electrical engineering. A bond is a low impedance connection between two or more metal objects. Ground is a point of reference for electrical potential, typically connected to the earth. When discussing electrical systems, it is important to use the correct terminology and concepts to ensure clear communication and safety. A bonding conductor's primary function is to create an electrically conductive path between metallic parts of an electrical system that are not intended to carry current under normal conditions. This path ensures that all bonded metal parts are at approximately the same electrical potential. This equipotential bonding is crucial for safety. It minimizes the risk of electric shock by reducing the voltage difference between accessible metal parts. If a fault occurs, such as a short circuit to a metal enclosure, the bonding conductor provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device, such as a circuit breaker or fuse, to quickly interrupt the circuit. The low impedance of the bonding conductor is key to ensuring a large fault current flow, which is necessary for the rapid operation of the overcurrent protection. The National Electrical Code, or NEC, provides guidelines for the sizing and installation of bonding conductors to ensure they can effectively carry fault currents. Specific NEC tables, such as Table 250.102 cone, and other relevant sections provide guidance on conductor sizing based on the size of the overcurrent protective device. Grounding electrode conductors, on the other hand, connect the electrical system to a grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. The purpose of the grounding electrode system is to provide a path for fault current to flow to the earth, helping to stabilize the voltage to earth during normal operation and providing a reference point for the electrical system's voltage. The grounding electrode conductor connects the system's grounded conductor, typically the neutral, to the grounding electrode. This connection helps to limit the voltage on the electrical system with respect to ground. While a grounding electrode conductor does have some inductance due to its length and the way it is installed, the inductance is usually not significant compared to its resistance, especially at the frequencies associated with typical fault currents. The impedance of the grounding electrode and the surrounding earth is typically much higher than the impedance of the grounding electrode conductor itself. NEC Article 250 provides detailed requirements for grounding electrode systems and grounding electrode conductors, including acceptable grounding electrodes, sizing requirements for grounding electrode conductors, and methods for connecting to grounding electrodes. The distinction between bonding and grounding is crucial for understanding electrical safety. Bonding focuses on creating an equipotential plane by connecting metallic parts, while grounding focuses on connecting the electrical system to the earth. Both bonding and grounding are essential for providing a safe electrical system. Misunderstanding the functions and characteristics of bonding conductors and grounding electrode conductors can lead to incorrect installation practices which can compromise the safety of the electrical system. For example, using an undersized bonding conductor can result in a higher impedance path for fault current, which can slow down the operation of the overcurrent protective device and increase the risk of electric shock. Similarly, an inadequate grounding electrode system can result in a higher voltage to ground during a fault, increasing the risk of equipment damage and electric shock. Therefore, It is important for electrical professionals to have a clear understanding of the purpose and requirements for bonding and grounding as outlined in the NEC and other relevant standards. It is also important to use the correct terminology when discussing bonding and grounding to avoid confusion and miscommunication. The term short circuit should not be used to describe a bonding conductor, as this implies that the conductor is intentionally creating a low resistance path between 2 points, which is not its intended function. Similarly, the term inductor should not be used to describe a grounding electrode conductor, as its inductance is typically negligible compared to its resistance. In summary, bonding conductors and grounding electrode conductors are distinct components of an electrical system with different functions and characteristics. Bonding conductors provide a low impedance path for fault current to flow between metallic parts, while grounding electrode conductors connect the electrical system to the earth. Understanding the differences between these components and using the correct terminology is essential for ensuring the safety and reliability of electrical systems. The NEC provides comprehensive guidance on the installation and sizing of bonding and grounding conductors. Always consult the latest edition of the NEC and other relevant standards when working with electrical systems. Now, let's delve into some specific examples to further clarify the differences between bonding and grounding conductors. Consider a metal enclosure housing electrical equipment, such as a panel board. The metal enclosure must be bonded to the electrical system's grounding system using a bonding conductor. This bonding conductor ensures that the metal enclosure is at the same electrical potential as the other grounded metal parts of the system. If a fault occurs inside the panel board, such as a wire coming loose and contacting the metal enclosure, the bonding conductor provides a low impedance path for the fault current to flow back to the source. This high fault current causes the circuit breaker protecting the circuit to trip quickly to energizing the circuit and preventing a dangerous voltage from appearing on the metal enclosure. Without the bonding conductor, the metal enclosure could become energized at a high voltage, posing a significant electric shock hazard to anyone who touches it. The size of the bonding conductor for the metal enclosure is determined by the size of the circuit breakers in the panel board, in accordance with NEC Table 250.102 Cone. Now consider a grounding electrode, such as a ground rod driven into the earth. The grounding electrode is connected to the electrical system's grounded conductor, typically the neutral, using a grounding electrode conductor. This connection provides a path for fault current to flow to the earth in the event of a ground fault. The grounding electrode also helps to stabilize the voltage to earth during normal operation of the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, in accordance with NEC Table 250.66. It's important to note that the grounding electrode system is not intended to carry significant current under normal operating conditions. Its primary function is to provide a reference point for the electrical system's voltage and to provide a path for fault current to flow to earth. The impedance of the grounding electrode in the surrounding earth is typically much higher than the impedance of the grounding electrode conductor, which limits the amount of current that flows through the grounding electrode under fault conditions. In some cases, multiple grounding electrodes may be required to achieve a sufficiently low grounding impedance, as specified in NEC Section 250.53 ATWO. This is particularly important in areas with high soil resistivity where a single grounding electrode may not provide an adequate path for fault current to flow to earth. In addition to bonding metal enclosures and connecting to grounding electrodes, bonding conductors are also used to bond other metal parts of the electrical system, such as metal conduits, cable trays, and equipment grounding conductors. These bonding connections ensure that all metal parts of the electrical system are at the same electrical potential, minimizing the risk of electric shock. Equipment grounding conductors, or EGs, are particularly important for providing a low impedance path for fault current to flow back to the source from electrical equipment such as motors, appliances, and lighting fixtures. EGC are typically run with the circuit conductors and are connected to the metal enclosure of the equipment. When a fault occurs in the equipment, the EGC provides a low impedance path for the fault current to flow back to the source, causing the circuit breaker to trip and de-energizing the circuit. The size of the EGC is determined by the size of the circuit conductors, in accordance with NEC Table 250.122. It's important to ensure that all bonding connections are properly made and are mechanically secure to provide a reliable low-impedance path for fault current. Loose or corroded bonding connections can significantly increase the impedance of the bonding path, which can slow down the operation of the overcurrent protective device and increase the risk of electric shock. Regular inspection and maintenance of bonding connections are essential for ensuring the safety and reliability of electrical systems. In addition to the NEC, other relevant standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, provide guidance on bonding and grounding practices. These standards may provide more detailed information on specific aspects of bonding and grounding, such as the design of grounding systems for sensitive electronic equipment. It's important to stay up to date on the latest standards and best practices for bonding and grounding to ensure the safety and reliability of electrical systems. In conclusion, bonding conductors and grounding electrode conductors are distinct components of an electrical system with different functions and characteristics. Bonding conductors provide a low impedance path for fault current to flow between metallic parts, while grounding electrode conductors connect the electrical system to the earth. Understanding the differences between these components and using the correct terminology is essential for ensuring the safety and reliability of electrical systems. The NEC provides comprehensive guidance on the installation and sizing of bonding and grounding conductors. Always consult the latest edition of the NEC and other relevant standards when working with electrical systems.